Hello, everyone, and welcome to today's graph reading group.
We're joined by Klein once again, and we're talking about flow matching, but now for molecules and doing this in an equivariant way. So equivariant flow matching. Let's go.
Yeah, so thanks a lot for having me again. I'm Leon Klein, a PhD student in the group of Frank Noe, and my work focuses on enhancing molecular simulations. And this time I'll talk about this more in the context of Boltzmann generators. So can you see my slides?
Yep.
Okay. Yeah, so today I will mostly talk about our paper Equivariant flow matching. So this joint work with Andreas Kremer and Frank Noe. And so we apply here our equivariant, what we call equivariant flow matching, to train Boltzmann generators. So what is the motivation for Boltzmann generators? So the goal is to generate equilibrium samples from the Boltzmann distribution. And we assume that the target energy here, U, is known, and therefore also the symmetries of the distribution are known. So classically, we do this with long MD simulations to generate trajectories that way. But the problem with these is that samples are of course correlated, and overcoming high energy barriers might be difficult. So transition between different metastable states might be rare and will require long MD simulations. So what Boltzmann generators do instead, they aim to accelerate the sampling, and they do so by sampling the states from the Boltzmann distribution independently. And the idea is to design them such that they somehow incorporate the symmetries of the underlying system into the Boltzmann generator. So as I promised, a quick intro to Boltzmann generators. So the underlying idea is that we transform a simple prior distribution, for example, multivariate Gaussian distribution, to a more complicated one, something like is close to the target Boltzmann distribution. So how do we generate samples then? Then we first sample from our prior distribution, which is easy. It's a multivariate Gaussian distribution, for example. Then we transform the sample with an invertible transformation. So this is most often a normalizing flow. And it's important that this transformation is invertible. And then we can transform these samples to the output distribution of the Boltzmann generator. And we train this invertible transformation such that the output distribution here of our Boltzmann generators is as close as possible to the target Boltzmann distribution. But in practice, they won't match. So we'll have somehow biased samples. But the cool thing now that we can do is that we rate our samples generated by the Boltzmann generator to the target distribution. As I mentioned, we require that we know the energy function of our target. However, we do not need the normalization constant. So we can evaluate the probability of the target distribution. And importantly, we also know the probability of the samples we generate with the Boltzmann generators because we use an invertible transformation here. And then we can compute for each sample the reweighting weights and obtain then unbiased samples from the target Boltzmann distribution. And the reweighting will be more efficient the closer our output distribution of the Boltzmann generator is to the target. So Boltzmann generators can be parameterized in different ways. Dogs in the office, nice.
Yeah.
Yeah, so the Boltzmann generators can be parameterized with different normalizing flows. So based on coupling flows or continuous normalizing flows are the two big things. And today, of course, I'll talk about continuous normalizing flows as we're going to do flow matching to train these.
Will you also be talking a little bit about how, like, maybe this guy right now, about what are the most efficient way to calculate the change of density with continuous normalizing flows, and what are some tricks that are maybe possible there?
Sure. Yeah, I'll mention this here. Although the tricks are actually harder to apply for us, but I think I know what you're referring to. So the concepts of continuous normalizing flows, so the ideas that we want to solve this initial value problem given by this ODE here, and the vector field, this is what we want to learn. And this can be arbitrary. This doesn't have to be invertible because we get the invertible transformation by the solution here. And this is how this transformation works. So we sample the initial state from our prior distribution. We then integrate this with our vector field starting from the sample until T1. And this gives us a sample from our output distribution. We could also stop in between and then get a sample from the distribution at the time between. But for the Boltzmann generator, we are interested in the whole integration. So, but this gives us only the sample. So what's now important that we are also able to evaluate the probability here. And this can be done with the change of variable equation. As you can see here, so the log probability is given by the probability of the prior sample, which is easy to evaluate. And then we have this term here, another integral, which is the divergence of our vector field. So of course, to evaluate this integral, we need to know this integration path here. So what one does in practice, that one integrates both of these together. And especially this term here can be quite expensive as it requires basically to evaluate Jacobian. So this scales with the dimensionality of the system. And how these continuous normalizing flows were usually trained is by maximum likelihood. So we would have to take the gradients, so we have to backpropagate through these two integrals here. And then there are some tricks to make this computation here more efficient to estimate this Jacobian term here. This is actually the trace of the Jacobian, the divergence of the vector field. So for training, this can speed things up a bit, but of course later we'll talk about a different training method, flow matching. However, when we sample with the Boltzmann generator, we cannot approximate this term because we need here an exact solution, otherwise the weights will be off. So this is a little unfortunate for the Boltzmann generators that for the sampling, we need to integrate these two together. And yeah, we cannot estimate this term here. And yeah, so as I mentioned, classically, the training is done by backpropagating basically through both of these, and we can use some black box integration solver, can be an adaptive method, a fixed step method. And yeah, this is called the adjoint method, how you can then get gradients for this vector field. And importantly, this vector field here is pretty arbitrary. We can use a simply dense neural network for it. So what we did then, because we want to incorporate the symmetries of the system into the Boltzmann generators. Yeah.
Can we maybe speak about that a little bit? Like, why don't why don't the intermediate steps now need to be a normalizing flow, so to say? Right? It's just we're.
So you mean for the Boltzmann generator?
No, here, and I guess also for the Boltzmann generator then. But why, if we're integrating this continuous change of variables formula, why don't we now need why don't we now need invertible neural network anymore?
Okay, yeah, that's a good question. So the parameterization is for the neural network is only, or the neural network only describes our vector field V here. So this I haven't touched. This I haven't mentioned here, how this is actually invertible. So I only showed the forward integration. However, for the other direction, we can simply here switch the integration direction and start from a sample T1. So, but we integrate the same vector field as before. So we only ever need to evaluate the forward of the vector field. We don't need an invertible vector field. So it's super flexible how we design this vector field. The invertibility comes from this integration here.
Okay.
And so how we design this vector fields to use an equivariant function for that. So what this means in practice, here's the equation for an equivariant function. So but consider, for example, configuration X with this vector field acting on this. This could, for example, also be a force. And then we do some symmetry operation, for example, a rotation. And then, of course, our configuration rotates and the vector fields rotates accordingly. So this is also what the behavior, for example, for forces would be. And the cool thing is now, when we use such an equivariant vector field, the whole transformation, the whole continuous normalizing flow becomes equivariant. So we have now an invertible equivariant function. And then we showed, this was a paper from 2020, that if we combine such an equivariant flow, and this doesn't have to be a continuous normalizing flow, but I just showed now here an equivariant flow based on continuous normalizing flows, that we combine this with a prior distribution which has the same symmetries as the flow, then the output will have, again, the same symmetries as the prior distribution. And this is quite powerful, as we now can control the symmetries of the output distribution of the Boltzmann generator. And what we then do, of course, is that we built an equivariant Boltzmann generator such that the symmetries of the output distribution match the symmetries of our target distribution, target Boltzmann distribution of interest. And we show that this is quite important, at least for the symmetry groups we look at. So here are some results. These are pretty old results for certain Lennard-Jones particles. So very symmetric systems, all particles are interchangeable, and we can rotate them as well. What you can see here are the energy distribution of samples generated with different Boltzmann generators. So here on the left is for an equivariant Boltzmann generator based on an equivariant flow. And on the right is a non-equivariant Boltzmann generator, where we use data augmentation to try to learn the symmetries. So green are the target samples. Red is the generated samples with the Boltzmann generator. And blue are the samples after reweighting. So you can see here for the equivariant flow, we have quite some overlap. The reweighting works really well, but for the non-equivariant one, it's much harder. So the distribution is way off, and also the reweighting works significantly worse. However, this was with a very simple equivariant architecture. So if we use any graph neural network, for example, the overlap will be perfect. So that these results don't look so good is just due to the very simple vector field we used. But it shows that this is quite important to include the symmetries of the system. So what we should use instead is some more expressive architecture for the vector field. So what we are using now are EFN equivariant graph neural networks. So they have a few upsides, and that's why we use them. So of course, they are equivariant with respect to the symmetries we're interested in, which are rotations, permutation, and translations. They are quite fast to evaluate, so we don't need to evaluate, for example, spherical harmonics. And they're also quite expressive, or at least sufficiently expressive for our task, as you'll see in the results. But a big problem was how do we scale these to larger systems, because the training of these continuous normalizing flows is so expensive, we have to backpropagate through these integrators. And so this is why we were quite excited about the flow matching. And I know this was discussed in this reading group before, I think at least twice probably, and you'll probably hear a lot about it in the future as well. I think it's quite a hot topic. But I will still quickly go through it. So it was introduced by different groups at the same time. And the main idea is that if we want to match it against a global target vector field, this intractable, what can we do instead is to match it against here a conditional vector field. So here, similar to diffusion models, we get the mean squared error between our vector field we're trying to learn and some target conditional vector field.
So the way I phrase it always is like we have and we want to learn some ODE that brings us from a prior if we integrate it to our data distribution. And now we have our we don't know such a vector field. We have no clue what such a vector field would be. But if we knew one, if we knew a UT of X, then we could just use this regression objective, like this flow matching objective. But we don't know any, but then these people show, yeah, doesn't matter. You can just use a conditional vector field, like this UT of X given Z. And this is actually something we can build. And yeah, we can just take samples from our data and from our prior and have this set, have it be the set, and then regress against that. And then we actually do end up with the same as if we were to regress against a UT of X.
Exactly.
Sorry, can I ask a question? Because this is actually something that I'm a bit confused about for matching. So they are saying that they're using the conditional, with UT conditional probability. But why is it a conditional probability if essentially initially two distributions are uncoupled? So from what I've seen, in the paper, they just sort of mix two distributions, right, to get an
maybe it gets clearer in a second. I think Hannes explained it quite well, the motivation for flow matching. I think I agree. It's quite an amazing result that we don't know this global vector field, but we can regress with respect to this conditional one. So maybe to answer your question, we can go through a very simple parameterization, which actually works quite well. So our conditional, the conditioning we're using here, the Z, is simply given by independent samples from the prior here and below and the target on top. So we are sampling from a joint distribution, but it's a product distribution. And then you can see this, our vector field, our conditional vector field actually depends on this conditioning, right? It's super simple. It's given by the difference between these 2 points. And the same is for the marginal distribution at time t. This is also given by, or depends on these 2 samples, and it's given by this Gaussian distribution here, where the mean lies on the connection line between these 2, which is simply a convex sum, and where t is the parameter between them. And then we have very small noise. And yeah, so what happens then, or what we can then do, and this tractable, as Hannes said, is that we sample our t between 0 and 1, and then we sample here a prior and a target sample. And with that, we can sample from this marginal conditional distribution here, because we have x1 and x0. And so we probably are a little off this line, and then the vector field at this point is given by simply the difference, and then we can regress our learn function to this. So
thank you.
This how
just one maybe a question about something slightly different from your work, I think. But if we want to couple 2 marginals that are already empirical, so like not some simple prior, but we actually are given like 2 data distributions from different domains, then is the assumption that after even if our Z, our conditional, is just a mix of independent samples from 2 distributions, is the assumption that those distributions somehow will get aligned if we are choosing an optimal transport map, or if we are trying to optimize this transport, so that essentially if we have, for example, like let's say data from let's say handwriting data for different digits, like digit of class 0 and digit of class 5, but written by a bunch of different people with their own style of handwriting. And the idea is that after matching the distributions flowing from 0 to 5, we will somehow align them so that we will be more likely to transfer from 0 written by a particular person to 5 written by the same person.
Yes, yes. Yeah, no, I think this is exactly what will happen. So I don't think this needs the optimal transport, or, I mean, maybe this is, okay, with the optimal transport, it gets more clear. I think I'll go over this in a second, but I think, yeah, maybe we look at this and then the question gets answered there. But in general, we can't use arbitrary distribution here. So the prior doesn't have to be a Gaussian distribution. And I think when we talk about the optimal flow matching, this is more related to what you're saying, that the person drawing the zeros, these samples will get matched to the same in the other distributions, the 5s drawn by the same person.
Okay, yeah, thank you. That's now much more clear. Yeah, it was just a bit confusing that Z is actually just a X, but I get it now. Thank you.
Yeah, great. Yeah, so exactly. So let's have a look at optimal transport flow matching now, or what I call optimal transport flow matching. I think there are different names for it. So, or what can happen, of course, if we randomly pick these samples from the prior and from the target and just pair them, that these vector field directions will cross. So this might not be desirable. So what we can do instead is that reorder these batches according to the Wasserstein distance. So here, this squared Euclidean distance is for the whole batch. And we want to find the optimal coupling between these two batches such that this transport cost is minimal. And we can do this with a very similar parameterization. So now the main difference is that we sample Z not independently from the two distributions, but according to this OT plan. And we don't need the global OT plan for this, which is, of course, completely intractable, but we can do it for mini batches. Okay, so this is great for us. We now have...
Let's maybe here have a brief thinking about what this means if we want to train a Boltzmann generator for that generalizes. What would the OT parameterization, how do we implement that if we train a Boltzmann generator that we want to train on many molecules and hope that it generalizes and maybe our batch contains samples from different molecules?
Let's postpone this question a little bit, but I think it's a great question. Yeah. Yeah. Let's first see how we can do it even for a single molecule, and then we can discuss how to transfer. It's a very interesting question. So what we have now, I showed we had already a recipe for Equivariant Boltzmann generator based on continuous normalizing flow. We can use an Equivariant graph neural network for the vector field. Then now with flow matching or even optimal transport flow matching, we have much faster training and we can scale to larger systems because we do not need this backpropagation through the integration. And we hopefully also get this optimal transport path, which allow us for significantly faster sampling because the integration for straight path is much easier. Okay, so let's have a look again for this Lennard-Jones system. And here on top, you can see a training pair generated with OT flow matching. Blue is a latent sample and orange is a target. And you can see it doesn't quite look like the optimal transport path. Some particles need to move quite a lot between these two samples. You can imagine there should be mappings which match a significantly smaller cost. And also during sampling, what's happening is different than the training, but this is because we are here averaging, we're learning an average vector field. But what happens is that we have these weird directional changes and we have really curved paths, so not straight at all. And especially with this change of direction here, the integration will be expensive as we need to do many small steps when the direction changes. Otherwise, we'll overshoot. So an adaptive solver needs to do many steps there, and the fixed size solver with fixed step size would require a lot of steps. So what is the problem here? The problem is that the system has too many possible permutations. So for these 13 particles, there are quite a lot of permutations. In order to account for them with the OT flow matching, we need infeasible large batch sizes. But for these curved paths, I think this is quite interesting that this is different from the training. So what we did, we looked at a much simpler problem with just 2 particles in 2 dimensions instead of the 13 and 3. And they're here connected by a double well potential. So the energy only depends on the distance between these 2. And there are 2 possible metastable states. And we train them such that the prior and target samples are always aligned. And then there's only one permutation. It's super easy to reorder these. So we learn here these perfectly straight integration paths. But if we do the opposite, if we always match samples such that they're not following the OT plan, but the opposite, so essentially, we want, for example, that this latent sample goes to this target and this latent to this, such that these paths cross. So this is what the model sees during training. However, what it ends up with are these integration paths. So instead of crossing the origin, what happens is that the direction changes. Even if it gets really close to the origin, instead of going across it, it will change the direction. And this is exactly what also happens for the larger system, for these 13 particles, but there the particles don't go really to the origin, but will turn much earlier because there's so many possible particles. So this is why you'll see these curved paths, but this for sure not what we want. So instead,
Quick question. Yeah. Why did the curved paths happen? Could you explain a bit more why they happen?
So how we train this here, in this case, is that this particle here should go either here or here, and this particle is supposed to be here or here. This is how we match the samples during flow matching. And then what happens, this resulting vector field was learned, is not learning that these actually cross the origin and go there, but instead, because for the vector field, which is permutation equivariant, it doesn't matter which particle is which. At some point, it'll just change the direction for the particle and send it back. This is what happens.
The vector field is permutation invariant, is that? Or is that what you said?
Sorry, it's permutation equivariant, yes. So yeah.
I see.
Yeah, and this then what happens?
Yeah, thank you.
Yeah, you're welcome. Good question. Okay, and here comes the idea of the paper in our equivariant, or what we call equivariant optimal transport flow matching. And so the first observation is that the optimal transport map between 2 invariant distribution is equivariant. And that's why we want to use the same equivariant Boltzmann generator as before, and it makes sense to use it. Now, the problem is, as we've seen earlier, we're currently not approximating the optimal transport map at all. So what we propose is that we compute the transport cost differently. So instead of using this the squared Euclidean norm, we are using this function here instead. So we are looking for the optimal alignment based on the symmetries of the system between the prior and the target sample, and then compute the distance between these two. And we show that this enables a very close approximation, even if you only use batches of the true underlying optimal transport map. And this is applicable to general symmetry groups. So maybe step by step how this works. So it's very similar to what I showed before with the flow matching. So we sample two batches of points independently from the prior and the target distribution. Then we compute the cost matrix for the whole batch. So this is a B times B matrix. And the cost is now given by this optimal alignment between pairs. So we have to compute or somehow align these samples for each entry of this cost matrix and compute this. So with normal OT flow matching, we would just compute the Euclidean distance here. And then we solve this OT problem. So pick the shortest or the optimal plan here, and then reorder these training pairs accordingly. And now importantly, we not only reorder, but we also keep the alignment which was used to compute here this minimal distance based on which combinations were picked. And this we can do this because these samples come from a distribution which is invariant under these group actions. So their probability doesn't change. And then we can do the same training as before, but we'll respect the symmetries of the systems and therefore get much closer approximation to the optimal transport map. So, and this work because we are, want to do it with Boltzmann generators, and there the goal is to sample small molecular systems or many particle systems. We focus here on the symmetry groups of rotations and permutations. Of course, translations are also important, but we can get rid of them by always being in the center of mass or center of position systems. So we don't care for the actual mass of the particles, only for the positions. And then we stay on the submanifold throughout the flow, and also prior and target distributions are mean-free. The problem is the modified cost function I showed earlier is actually intractable for rotations and permutations. So what we do instead, that we approximate this. So how do we do this? So there are different ways to do this. One thing we tried, and this worked best in our experiments, to first compute the optimal permutations between the prior sample and the target sample with the Hungarian algorithm, and afterwards align these samples by rotation. So here's an example. So on the left is again this Lennard-Jones system with 13 particles.
Yeah.
Yeah.
If we go back to the slide, so the cost that we use for our Hungarian algorithm, is that after RMSD? So that's without RMSD alignment?
I mean, it's something similar than compared to RMSD, but yeah, these are not aligned.
Okay, so yeah.
So the problem is that the prior samples are not ordered at all, so they're not close to a real molecule. So it's not that easy to align these samples. For example, the backbone.
We have the same in the chat now. Why can't we decouple the rotation and permutation? But I guess that's what you're addressing right now.
So with decoupling, yeah, I mean, and of course we should search over both, right? But this is a not tractable thing to do. So this is why we decouple these, and I will show different approximation methods we tried, which we could use here. But the one I'm showing now, where we first permute and then rotate, although of course this probably won't give us the solution to the underlying problem, but it actually gives a quite good approximation, at least on average. So here is an example. So on the left, we have the optimal, again, a pair which was reordered based to OT flow matching. And then if we only here align the permutation and rotation of the samples, already you can see the overall transport cost will be much smaller. And this is without all this other stuff happening that we solve the OT problem for all different sample pairs. So overall, the mean batch transport cost, so the mean transport cost for a batch of samples is significantly lower and about 4 times smaller for our equivariant OT flow matching compared to simple OT flow matching. And now about the different approximation methods. So these are all assuming that we decouple the rotations and the permutations. So first, naive flow matching, what I mean with this, we don't reorder at all. So this set of costs, the highest transportation cost. Then with the OT flow matching, we reorder the samples, but do not care about the symmetries. And then all these here below are some approximation methods you also see on the right. So the blue one is the one we ended up using, which is first doing the permutation and then the rotation. And interestingly, doing it the other way around, first the rotation, which is the orange one, and then the permutation, but also doing this 2 times, if you started with the rotation, is both worse than doing the permutation first. What then helps is doing the permutation and rotation multiple times after each other.
How can doing it 2 times be worse than, like, I mean, then you also...
You know, but the problem is, so, okay, sorry, this is for alanine dipeptide, so, but the results for the Lennard-Jones system are actually quite similar. So what happens for alanine dipeptide, or what can happen, for example, that by first rotating it, because the permutations are completely off, you might rotate it to completely wrong alignment, right? For example, 100 degrees, 180 degrees off, and then you do your permutation, then everything is quite fixed. So the next rotation you will be doing can only wiggle a little bit because the permutations are already quite good. And then doing another permutation won't help you again. So doing the permutation first seems to be a better way, but it's an excellent question, and that's what we ended up. So that's why we ended up doing first the permutation and then the rotation, because doing it more often didn't change that much. And you can imagine this, doing this for every batch is already quite costly, and doing it twice would be twice as expensive.
I would like to see where doing only the rotation falls here.
Oh, okay. Yeah, I think we tried this. This also interesting, yeah. I agree.
Because to me, intuitively, I would feel like rotation is basically what matters the most, and doing the OT is nice to have, maybe.
Do you mean the permutations? Yeah, but you have to imagine all the permutations are completely random. So, and you have to match, even for the Lennard-Jones system, right? You probably don't find a really good alignment just by rotations because the permutations are so off. So I think the permutation is much more important than the rotation in this case. Yeah. And what we call here a reference is that we have a lot of candidate rotations first, and then we do 3 permutations and rotation afterwards, and then look where we get the minimal distance. Okay, so maybe now, Hannes, after I explained now how this equivariant OT flow matching works, you had a question, maybe you repeat it again about transferable Boltzmann generators and how this would work, right?
Yeah, so right, if we in our batch we always have samples from the same molecule. But now what
Yes.
if we want to train a generalizable Boltzmann generator and I train on many molecules and want to generate their 3D structures and sample their Boltzmann distribution, then
Yeah.
I would have batches where the samples come from different molecules. And
Exactly.
how do I then do the OT?
Yeah, no, that's an excellent question. So it may be important to note just before I have mentioned that the Boltzmann generators can be both trained in internal coordinates and Cartesian ones, and it's much harder to make a transferable Boltzmann generator in internal coordinates. And here we focus on Cartesian ones. But Hans asked a very good question. So if there are different molecules in a batch, how do we do OT flow matching then? And so the only solution we have currently, and this what we're trying, is that we compute batches only for the same types of molecule, and then do the equivariant OT flow matching for these batches. And then during training, we can pick samples from different batches and use them together for training. So this reordering doesn't happen during training, but before. And for the training, we'll then get batches which consist of samples from different previously reordered batches. Does it make sense, Hannes?
Yep.
Yeah, and this actually also what we do even for the same type of molecule, because this can be done in parallel really easy. Each batch is completely independent from the other ones. So we can do this data preparation on a lot of CPUs, which are usually much more available than the GPUs. And yeah, align the data that way, because this slows the training down quite significantly otherwise. I can imagine if we are scaling to even larger systems, the Hungarian algorithm will be quite expensive, and we have to do it for every possible pair in the batch. Yeah, there's another question.
Yeah, Leon. So I was curious about the Boltzmann generators. You started talking at the beginning. Like one thing I don't understand is, don't you need to have samples from the target distribution that you're trying to learn, at the beginning? And how do you, and how do you get those samples to start with?
Excellent question. Seems a little counterintuitive, right? We are trying to sample from Boltzmann distribution, but here's flow matching. I explained we need samples from the prior and from the target. So what we need is actually that we have samples from at least short MD trajectories or some MCMC method to train the Boltzmann generator.
But then if you want to sample all the metastable states, then you need to have samples from short MD trajectories covering all those metastable states, right?
Definitely. And this is also why Hannes' questions from before was very important, because I think, so you're completely right. It's then hard to beat MD with it, is you need an MD simulation first in order to train the Boltzmann generator, right? Yeah. Even if you could argue, okay, you only need short MD trajectories, but you from each metastable state, for example, this could work. I will also show later a slightly modified version of this, but in general, the big goal would be to have a transferable Boltzmann generator, so that you would have to have some MD simulations for some training molecules, train your Boltzmann generators, and then you could sample on unseen ones where you then don't require any training data. This is a little similar to what we did in the time warp project, although there we didn't sample directly from the Boltzmann distribution, but only proposed large steps in time. But yeah, this is definitely a problem for the Boltzmann generator that require this training data. Although what Boltzmann generators, how these can be trained as well, is only based on energy. So you're sampling from your prior distribution, push your sample forward, and then evaluate the energy. However, this is not compatible with flow matching. So for that, you would have to, again, backpropagate through the whole integration path, or use a Boltzmann generator not based on continuous normalizing flows, but on coupling flows, for example, where this backpropagation through the whole flow is much simpler.
don't think I got the last part, but by pushing it forward, you mean pushing it through the flow model?
Exactly, the flow, and in our case, with the continuous normalizing flow, you have to do the full integration. And then you evaluate the energy, and then you can get a gradient signal with that, and then you have to backpropagate again through the whole integration part. This is possible, but quite expensive.
Another really good question? I got about metastable states and how about saddle points? How are those sampled and learned by the Boltzmann generator?
You mean like transition states?
Transition states, exactly.
Yeah. This might be hard if you don't have data there. I mean, the Boltzmann generator will learn some connection, but as they are usually not that frequently sampled, it's usually hard for the Boltzmann generator to sample these. But usually, if we are more interested in like free energy differences or how likely different metastable states are compared to each other, these states, these transition states don't matter that much.
And then the main thing at the end is that like the Boltzmann generator can give you independent samples, right?
Yes.
From your energy function, like. You cannot generate a trajectory per se, like MD does, for example.
No, this is not for the kinetics. This is there are also possible ways to use a Boltzmann generator in a accept reject frameworks, but usually the idea is to get just samples from the equilibrium distribution. And importantly, even if you train on biased samples, with this reweighting, if you have coverage everywhere, you'll get really samples from the unbiased equilibrium distribution.
I didn't follow the last one, I think, sorry.
So now we mentioned that you can train a Boltzmann generator with biased training data, right? For example, only small trajectories in the metastable states, but the weight between these is not right. So the Boltzmann generator the output of the Boltzmann generator will be biased as well, will be a biased distribution, but with this reweighting, you can actually debias the distribution, so you get then really samples from your unbiased target.
Yes. Gotcha. Yeah, thank you so much.
Yeah, you're welcome. Then let's have a look at some results. So first, again, this Lennard-Jones system, but now with a lot more particles, in this case 55. So we picked 13 initially because the global minimum is a nice icosahedron with one particle in the middle. And with 55 particles, we get another icosahedron layer around for the global minimum. And you can see here integration path for trained Boltzmann generators. On the left, it's with OT flow matching, and on the right is with our Equivariant optimal transport flow matching. And for your OT flow matching, you can again see we have these change of direction. So we first go towards the center and then go outwards again. And for the Equivariant OT flow matching, the paths are pretty straight and the direction changes are not that severe. And this, of course, because the transport cost during training is already much smaller. So you can see here on the right, in blue is the mean batch transport cost for OT flow matching. And for the Equivariant flow matching, it's about 10 times smaller. And this results also in shorter integration path, as we have just seen. So in green are the integration paths, so it's simply the path lengths for all particles, is the one for the Equivariant OT flow matching, and orange one is for the normal optimal transport flow matching. And what I mean here with the optimal transport map, because of course the global optimal transport map is intractable, but what we use here simply, we look at prior and output samples from the Boltzmann generator and draw a straight line between them and take the distance for those. So if we match these OT samples, or what I call OT samples, then our integration path would be straight lines. So you can see we are a little bit off, but quite close for our Equivariant OT flow matching. And this helps us during inference, so when we sample with our Boltzmann generator. So I mentioned earlier, we can use different types of integrators to integrate our vector field. So a popular choice are adaptive solvers. And we compare here a Runge-Kutta integrator, which has a fixed step size, with an adaptive solver with an adaptive solver, and we compare the error this Runge-Kutta integrator makes for different number of integration steps. So you can see even for quite a significant number of integration steps, the OT flow matching has quite a significant integration error, while the equivariant OT flow matching, even for 20 steps, will get the same results as with the adaptive solver. And this, of course, again, because for the OT flow matching, we have this change in direction and this curved integration path. So for sampling, for the Lennard-Jones system with 55 particles, we can use this Runge-Kutta integrator instead. And then what we're interested in are effective samples we're generating with the Boltzmann generator. And we show them here dependent on the number of function evaluations. The function evaluations are here simply the evaluations of the vector field. You can see that the equivariant OT flow matching produces more samples, more effective samples than the OT flow matching with the same integrator, which is the adaptive one. But if we use the Runge-Kutta integrator, we get even more effective samples per function evaluation, which are similar to, also proxy for the time needed for the inference. So this is exactly what we wanted, right? So now we have a framework which includes the symmetry of the system and allows us to get quite straight integration paths to speed up the sampling of the Boltzmann generator. And then we also did this for a molecule, so for alanine dipeptide. Here we have the problem. So initially wanted to do it with a classical force field. The problem is that these force fields depend on the ordering of the atoms. So based on they're expecting a certain ordering based on the topology. But with the Boltzmann generator, as our prior distribution is a Gaussian and the same particle types, these particles are interchangeable and randomly positioned. The output of the Boltzmann generator, there the permutation will be completely random. So it's really hard to compute the energy for these. So what we do instead is that we use a semi-empirical force field where the permutation of interchangeable particles doesn't matter. And this also goes a little bit in the direction that we don't actually need samples from our target distribution to train the Boltzmann generator, because we do the data generation a little different than just simply doing a long MD trajectory with respect to the semi-empirical force field. So what we do, we use the classical trajectory, which are often available for a lot of molecules. So we take a trajectory generated with the classical force field. Sorry, what's their question? No? Okay, so we generate a trajectory with the classical.
Can you quickly say what is the difference between a force field and a semi-empirical force field?
Yeah, this includes some approximation of more quantum terms.
Like the Huckel model and stuff like that?
I'm not that sure. I would have to check. So we are using the XTB force field. I'm not exactly sure what approximation they use.
But there are electronic degrees of freedom then in the representation, not only nuclei, just some electronic information.
I mean, it's an approximation for these. So it's much more expensive to evaluate this force field. Yeah. Oh yeah, this important thing I should have mentioned. So I think it's 100 times more expensive than a classical force field. So generating MD trajectory would be much more expensive. So what we do instead, we generate this classical data, and then we pick some training data. And for these training samples, we run really short trajectories with this semi-empirical force field. So we relax these samples essentially. And what we get then is that we have a biased training set for the samples. And we didn't require a long trajectory from our target Olsen distribution. So this goes a little bit in the direction that we don't require samples from our target distribution for training. Yeah, so I mentioned we have a biased distribution, but although the Boltzmann generator then of course also learns a biased distribution, due to the reweighting, we're able to reweight to the unbiased target distribution. Okay, so here, because it's quite a small molecule and there are now different particle types, and for the oxygen and nitrogens, for example, there are only two possible permutations. Our equivariant OT flow matching, the benefit of this is not as pronounced as before. In fact, you can see here for the sample path lengths, they are quite similar. So maybe for these small molecules, it's not that important to use our method. So and you can see here in the results, actually, at least for how we did the training, OT flow matching performs actually a little bit better on the negative log likelihood and also effective sample size than our equivariant OT flow matching, while the path length is only a little bit better. But these shows, and this is quite exciting, it's the first time a Boltzmann generator in Cartesian coordinates for a real molecule. Prior to that, this was only possible with an internal coordinate parametrization. And it's worth to note, though, that there's also concurrent work, which also achieved a Boltzmann generator in Cartesian coordinates, and they use coupling flows instead of continuous normalizing flows. So they're the setup is a little different, but now it's possible to have Boltzmann generators in Cartesian coordinates.
What sort of experiments do those folks do? Like what systems do they?
So they look also at this Lennard-Jones system, but they also look at alanine dipeptide, however, at a much higher temperature from what I've seen. So I think it's 800 Kelvin, and we are looking here at alanine dipeptide at room temperature, which is of course more difficult.
And can you say something about the likelihoods computed here? Are the likelihoods that they compute like better and more easy to use for reweighting, or are your likelihoods more accurate?
So I think for the alanine dipeptide results, these are not relatable. So as I mentioned, it was concurrent work, so we use different data sets. But I think coupling flows, if they are expressive enough, this was usually the problem with coupling flows, that weren't expressive enough to sample these efficiently. If they are expressive enough, they are usually faster to evaluate during sampling. So even if they get a small effective sample size, they might be preferable over continuous normalizing flow simply because you can sample many more samples in the same time. Yeah, but I think it remains to be seen how they actually compare. And we also wanted to validate our alanine dipeptide results. So we did an additional training where we're interested in the free energy projection along the slowest transition. So here you can see the Ramachandran plots of the two important dihedral angles. And the slow transition between or along the sphere angle and between the state between the 0 and 2 phi angle and all the rest. And what you can see here is probably not the Ramachandran plot you know for alanine dipeptide, but to train the Boltzmann generator, we had already this bias data, but we are writing the data additionally for training, such that the positive phi state is more likely because the reweighting from a biased distribution where we oversample the unlikely state, it's significantly easier. So you can see here the Boltzmann generator very well reproduces this weighted unbiased distribution. Now here you see the energy distribution of samples produced with the Boltzmann generator, which have quite a good overlap with the relaxed MD samples. Although, of course, these relaxed MD samples, they're not coming from the equilibrium distribution, so they are biased as well. So the true distribution might be a little different. But what we can do to evaluate our Boltzmann generators is look at the free energy projection and do an umbrella simulation along the slowest transition, so this phi angle. This is much faster than doing along a MD trajectory, and also can be done somewhat in parallel. And what you can see here, so this free energy projections, basically the projection of this Ramachandran plot to this axis. And for the Boltzmann samples now, these are reweighted with respect to the target, which is the semi-empirical force field. And you can see here, the free energy distribution matches very well. So here again in the transition states, which are these, where we have only a few samples, that's a little off, but we usually don't care that much for these. And also, if we compute the free energy differences between these two possible states, which is shown here below, they agree very good. So the umbrella simulation and the Boltzmann generator. And you can really see that our training data was biased. So for this relaxed training data, the free energy difference is significantly different. And this is also the green line here shown in this plot. And for the classical MD, it's even more off. Okay, then to sum things up, so I talked about flow matching and our Equivariant flow matching objective, which includes the symmetries of the systems in the flow matching framework. Then we applied this to Boltzmann generators and had for the first time a Boltzmann generator in Cartesian coordinates, where we had very good in Cartesian coordinates for molecules, where we showed very good agreement here with the target free energy surface. And then we've seen that when scaling to a larger system, maybe more symmetric system like this large Lennard-Jones cluster, our Equivariant OT flow matching objective is crucial in order to get these straight or close to straight integration path, which allows us to sample significantly faster. And that's it. Thanks a lot for listening, and I'm very happy to answer more questions.
Okay, thank you for answering so many already, and
yeah.
I like it. What do you think in the? Oh no! First, what is the? How do you like? What are the numerical tricks for integrating the probability for getting the likelihood? Like, is there anything required, or is this
no? Then, yeah. I mean, then you can do a lot of things based on how straight your integration paths are. If you don't need the likelihood, so then with the straight path, you could even think about an Euler integrator, I think.
What does this have to do with calculating the likelihood?
This year, if I mean, if you only need the likelihoods somewhat right, then you can also use here. So how I understood the first question was, we don't care about this at all, right? We only want samples. For example, images,
no,
we don't care
my
about.
My question is, when calculating the likelihood, are there any numerical tricks to get better likelihoods, to have lower approximation error and so on?
Oh yeah, this I'm not sure about. So what's usually done is to use the Hutchinson estimator for this Jacobian trace, which has a much better scaling. And this gives I'm not sure about the exact estimate, but it's pretty good. But we tested it for reweighting and it doesn't work at all. So the weights will be super off, but what you can very well evaluate this if you're just interested in the likelihood, some average likelihood, for example. This works well.
Okay.
But individual weights are not so much.
Right, so for your likelihoods for reweighting, how do you get those?
Oh, the likelihoods for reweighting, exactly this equation. We have to integrate this. And then we can speed this up if we can use some fixed step type solver, do larger steps, larger integration steps. That's basically what
so
we
you
can do.
don't use Hutchinson trace estimator.
No.
You need to do the exact thing.
Yeah, maybe there's a way. I don't know. To approximate this and make the integration faster. What we did initially, where the results were not so good, that we had an analytic form for this Jacobian trace, so that way we didn't have to compute it. And then it's of course much faster, that you don't have to take here the derivative during the integration. Yeah,
that's nice. Then can this be used for coarse-grained systems? Is Denise asking?
Oh yeah, that's a good question. So in theory, for sure, it could be used for coarse-grained systems. Yeah, simply use the coarse-grained, whatever coarse-grained beats you has as the coordinates. However, then you're probably not that interested in this change of variable equation because you don't know the target energy of the samples. And then the reweighting, I think, doesn't really make sense. But you could still use flow matching and generate coarse-grained samples that way. I think this should work.
Okay. Then if folks want to use this, the code is available.
Yes. I'm not sure if the open reviews for NeurIPS are already available. If not, the code should be available soon in the BG Flow framework, like in the coming weeks. Or if you need it now, you can also shoot me an email and then I'll send you the code we submitted.
Okay, very nice.
And the datasets I think are linked in the paper. Yeah, the datasets are available.
Cool. Then Dom, do you have any last questions or anyone else? Then I would say, Leon, is there any future work you want to point to or any advertisements you want to make?
Yeah, I think the transferable Boltzmann generator are very, very interesting. And yeah, we'll see. Maybe you'll hear from me again about these, but we'll see how it works out.
Yeah, many thanks to Leon for this nice presentation about equivariant flow matching. And yeah, as he says, maybe generalizable someday. And if that ever happens, then we will for sure have him on here again. So don't miss that. And check out the stuff in the description to stay updated either via our mailing list or join our Slack channel or stuff like that. See you, friends of the sun.